Hey everyone, I am Miss Hu, your physics teacher. In this video, we're going to go through the concepts of base quantities, derived quantities, and SI units, including how to use SI units to check the homogeneity of equations. This video is designed for students who will be taking the AS portion paper of A levels of Cambridge Physics. Now, there are many different types of units. The main types of units that you should be aware about are SI units, metric system, British Imperial, and US Customary. Now in this video, we're not here to discuss these different type of units. The list I've introduced here is just for you to be aware about. Just to show you a meme about a comparison of different types of units. Not everyone is comfortable with using the metric system. So anyway, this is a little joke for you. It's funny, but at the same time, it's kind of true. But anyway, we're not here to poke fun at anybody. This is just a good-natured joke. So in terms of units that we're going to be focusing on in our syllabus, we'll be focusing on SI units. What are the SI units? So the SI units is an international system of units. SI units are the standard units of measurement used in science and industries. It is a standardized system of measurement that is universally understood and easily compared. So we have to use standard units when it comes to research, especially when we want to compare our results. Because if we are using different units, then it makes it very difficult for us to be able to share knowledge and to compare information. For example, if you were to take measurements and in one country the measurement of a particular object is 4 feet and in another country you say that it's 20 centimeters, how do you know which one is longer or shorter? So if you use two different sets of units, it's very hard for people to be able to make that comparison. And in order to be able to make a fair comparison, you'll have to bring both down to the same unit. So that is why for scientific industries, the standard unit we have chosen to use are the SI units. Now let's go into the concept of base quantities. By now you should know what physical quantities are. So physical quantities are the properties ascribed to objects which can be measured. So base quantities are physical quantities which cannot be derived from any other physical quantity. They are the fundamental physical quantities chosen by convention. So as you can see in this list, there are only 7 base quantities. You have to be aware, of course, there are possibly thousands and thousands of physical quantities out there, some of which you would never even hear in your lifetime because every industry has its own specialized physical quantity. However, it is generally accepted in the entire world and in all industries. These are the only 7 base quantities out of those thousands and thousands of physical quantities. All other physical quantities that exist are derived from these base quantities. So these are the 7 base quantities and their corresponding SI units. Length, measured in meters. Time, measured in seconds. Temperature, measured in Kelvin. Mass, in kilogram. Electric current, in ampere. Amount of substance in mole, and luminous intensity in candela. Now of course remember that each of these physical quantities do have other units which can be used to express the values. The list here shows us the selected SI unit for each of these respective base quantities. And yes, you do need to know the 7 base quantities and their corresponding SI unit. Now let's go into derived quantity to have a clearer understanding of what they are. Derived quantities are physical quantities which are derived from other physical quantities through multiplication and or division. Let's take a look at some examples so that you can understand this better. For example, if you were to calculate the volume of a cube. Now of course you can measure a volume of a cube using the water displacement method, but we are here to talk about the calculation methods. So the general formula to calculate the volume of a cube is length times width times height. Now we're going to bring this down to the same physical quantity so that it's easier to measure. When you look at width and height, they're basically just names for different types of length. So we have different names because it helps us visualize which part of the cube that we're measuring. Length, width, height. But if you look at the types of measurement, they are basically all different types of lengths. So we're going to substitute this with length times length times length, which gives us length cube. So as you can see, volume is actually a brand new physical quantity that has been obtained by multiplying length 3 times. And there are 3 different types of lengths. So the length value may not be identical, but I've put here length cube just to help you visualize that basically we've taken the 3 different types of length and multiplied them. So from here you can also derive the SI unit of a volume. If the SI unit of length is meters, this is why the SI unit of volume is meter cube. Let's go through another example. Speed. Now the general formula for speed is distance divided by time. So as we know, distance is also a type of length. And if we were to try to derive the unit, Distance is in meters, time is in second. That's how we get the SI unit of speed as meters per second. You can write meters per second this way, m/s. In AS and A levels, we prefer to write it this way as m as -1. However, either way you write it would still be accepted as long as the unit is correct. So you can see here, speed is a brand new derived quantity obtained by taking two different physical quantities and dividing them. That's what it means when we say here that derived quantities can be derived through multiplication or division. It can also be a combination of both. For example, calculating density. The general formula for density is mass divided by volume. Now, volume is also a derived quantity, as you can see from this initial calculation, which means we can substitute this with mass divided by length cubed. So, density is an example of multiplying and dividing different physical quantities to obtain a brand new derived quantity. We can also derive the SI unit from this equation. If the SI unit of mass is kilogram and length cube is meter cube, we would get kilogram per meter cube. Again, you can write it in either form. In AS or A levels, just a reminder, we prefer to write it in this form. Now, you should be aware that SI units doesn't necessarily mean that they have to be base units. You'll find that some derived physical quantities do have their own SI derived unit. For example, force. As we know, the general formula for force, based on Newton's second law of motion, is mass times acceleration. Now, from this equation, we can derive the units for force. If mass is kilograms and acceleration is meters per second squared, we can get the unit of kilogram meters per second squared. Now, these are SI units, but these are SI base units. Force has its own unit, which is Newton, and the accepted SI unit for force is Newton. While it's not wrong to write kilogram meters per second squared, the SI unit of force is actually Newton, and it's preferred you write it in Newton because it's much easier to comprehend. Another example of this is pressure. The formula for pressure is force over area. So now we know force is Newton and area should be meter squared, giving us the unit of pressure to be Newton per meter squared. However, pressure does have its own SI unit, which is Pascal, or you can write PA for short. Now let's look into the homogeneity of physical equations. A homogeneous equation in physics refers to an equation where the units on both sides are the same. So from here, we can compare the units on both sides of the equation. We know the SI unit of force is Newton, we know the SI unit of mass is kilogram, and the SI unit of acceleration is meters per second squared. So what this tells us is that 1 Newton is equal to 1 kilogram meters per second squared. So Newton is equivalent to kilogram meters per second squared. Now some of you might be thinking, wait a minute, you said the units on both sides are the same. What it just shows us here is that they have the same value. Now let's look at another example. Pressure. So we know that pressure equals to force divided by area. The SI unit for pressure is Pascal, while the SI unit for force is Newton and area is meter squared. We can therefore state that 1 Pascal is equal to 1 Newton per meter squared. Now from the earlier equation, we know that Newton is equal to kilogram meters per second squared. So if we were to put this into the equation, we'll get kilogram meters per second squared divided by meter squared, and simplifying this, you'd end up getting Pascal equals to kilogram per meter per second squared. Now one thing you have to understand when it comes to using equations is that if you were to compare the homogeneity of the physical equations, you have to write them in SI units. So yes, the equations are built on SI units. So you cannot just take the equation and randomly put different values inside using different units. If you want to write them in SI units, every single variable in that equation should be in SI unit. Let's look at one more example, and this should show you clearly the homogeneity of all these different equations. When it comes to calculating energy, there are many different types of energy and therefore many different equations. So on this slide, I've only put 3 formulas for calculating energy. On the left-hand side here, we have the formula of kinetic energy, which is half mv squared. Now, when expressing the SI units, for a constant like half, there's no unit, so that's why it's not even written here in the unit calculation. So we're going to take only the units of the variables, which are mass, which is kilogram, and v, velocity, which is meters per second. So based on the equation of half mv squared, we will get kilogram times meters per second squared, giving us kilogram meter squared per second squared. So this is the SI base unit for kinetic energy. Now let's look at gravitational potential energy. The formula is mgh. Let's look at the units based on this equation. So mass is kilogram, g, which is gravitational acceleration, is in meters per second squared, and h, which is height, is in meters. So kilogram times meters per second squared times meters gives us kilogram meter squared per second squared. For elastic potential energy, the formula is half Fx. F is force, which is Newton, and x is extension, and the SI unit for extension is meters. From this equation, we'll get the SI units as Newton meter. Now let's break Newton down into SI base units. From an earlier slide, we already know that Newton is kilogram meters per second squared. So we multiply this with meters, giving us kilogram meter squared per second squared. Now, as you can see, whether you're calculating kinetic energy, gravitational potential energy, or elastic potential energy, all of them end up having the same SI base units. So since we know that the SI unit for energy is joules, from here we can conclude that the SI unit of joule is equal to kilogram meter squared per second squared. Knowing how to use a homogeneous equation like this will enable us to be able to derive units of unknown variables from an equation. To understand that further, I'll cover that in another video where we'll go through some examples on how to solve questions. And that is it for this video. So, if you found this video to be educational and helpful, do click like and let me know in the comments below how you have found this video to have helped you. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. For notes, quizzes, and syllabus updates, check out my website at physicsrocks.com. Do watch my videos on other topics on my YouTube channel, which you might find helpful. Subscribe for more free physics lessons from your physics teacher, Miss Ho. Happy studying!